Perhaps the most important part of a space voyage is coming home safely. The spacecraft must survive the extreme heat and friction of re-entry into the Earth's atmosphere. Scientists and engineers create heat shields to protect the spacecraft. But how do they know it will really work? The answer is the ArcJet facility.
Okay, well, thanks everyone for coming. This is actually my first time being at a Spitzer, and I'm actually presenting. I don't usually come to campus on Fridays, but I really do appreciate everyone who could come today. Thanks, Aaron, for filling in for Derek, who couldn't be here. I appreciate all the tech stuff. So I'll introduce myself. I'm Dr. Doug Cadrone. I've actually been with the physics department here for, it's going to be 10 years, actually. So it's been a rewarding, long lecture career here. So I'm excited today to present some of the work I've been doing with a startup company, not actually located in the Bay Area. So this is a company, we found each other actually through networking through Zoom. It's an interesting world now because you could work with people. And I finally met my CEO first time in person after 2 years of working with him. So luckily I wasn't catfished. He was who he looked like on Zoom. But so yeah, that's the world we live in today. So I'm going to talk about our work. Our company is Baldwin Aerospace, and we're attempting to go ahead and build a miniature ArcJet facility in the Bay Area. And I'll explain what it does and why we would care about that. So we'll go ahead. I'll just go through also the overview for what I'll talk about. So I'll give everyone a background about ArcJets themselves, because I know this might not be a typical physics Spitzer in the traditional sense that you guys are used to. So I'm going to go through what ArcJets are, the purpose of it, why we care about them, and a little history again, what they're used for today. And then I'm going to talk about our design. So what we're planning to do for our facility and what its capabilities will be. We'll look at some flow simulations. So right now we're limited to modeling work. So we've been doing some simulations to get an idea of what kind of flows we could handle in our ArcJet facility. The heat loads are very critical. We're going to look at how those are distributed through the arc column and the converging diverging section of the arc heater. Then I'll talk about what we plan to do in the future a little bit. I'll summarize everything at the conclusion, and then I'll open it up to everyone if they have questions. So let's start from the beginning and just talk about what is an ArcJet. So this is an ArcJet heater, not to be confused with like an ArcJet propulsion device. There is actually propulsion using ArcJet, but this is a heater, which is used mainly in industry to recreate entry environments for spacecraft to look at thermal protection system materials, which I'll talk about later. But here's the basic idea behind it. So what you have for your ArcJet is a cathode anode configuration and a high power supply. So large ArcJets, like the ones they use at NASA to test TPS for like the space shuttle, Apollo missions, those are megawatt classes. And then there's scaled down ones, which are in the kilowatts. Kilowatt ArcJet heaters are typically run by a power supply. That power supply could be something as simple as an arc welding heater supply that you could buy off the shelf. So that's what would be powering ours, for example. So anyhow, you have your negative electrodes, your positive electrode. You inject some gas here. And basically, you create a discharge at high power, high current, and you basically take that gas, swirl it, and then it's ejected out a converging, then diverging section. So what happens here is actually the gas slows down as it's constricted to the throat where it chokes. And then after it reaches Mach 1, it's accelerated out supersonically out the throat here. So this is the diverging section. This is how basic rockets work. It's the same idea.
Question, this is also how like an arc welder works.
Arc welder is similar, except you will not have this section. There's no need for a converging, diverging section because you're not trying to accelerate. Yeah. But other than that, it's pretty much the same thing.
So okay, I'm trying to. Yeah. What you're doing is you're injecting a neutral gas, right?
Yeah, air.
And then
or argon. Yeah.
Right. And then the cap you strip, you create an ion-electron pair or ion-electron pairs, and then because of the positive charge there, you're basically shoving those gas. The electric field shoves those gases into a small hole, and then they come out the other end, and they're compressed and heated. And
basically, so this cathode gets heated, and it thermionically emits the electron. Electrons come off the surface as well as encountering the gas.
Okay.
And though there's high pressure, high temperature, then like any rocket, it just
so are you ionizing the gases to be a negative charge so they'll go through the hole there?
No, so you don't want charge separation ideally. You want it to be a neutral. So
what? So how are the gases being forced to go into the hole?
That's what happens in a converging, diverging section. That's how a rocket works. So the gases are heated. There's an arc discharge, high pressure, and they're pushed basically through this converging section. And then they're accelerate out the diverging.
Yeah. So like, I'm just thinking about like the mass of the electrons compared to the mass of the protons. And like, I'm imagining that if there was some ionization, that the electrons would be accelerated like a lot more because of their lower mass.
Yeah, that could be
true. And so the idea is that you're trying to keep them as neutral particles. So like,
yeah, I mean, there is going to be some ionization, but yeah, you want to keep things, you don't want like unbalanced charging if you could, stop that. But yeah, I mean, basically you do what you can to recreate the entry conditions. So it's a quasi-neutral plasma, but so that's the idea for how we have the flow. And so basically the kinetic energy is directed out, and that kind of dictates the energy performance from the simple equation, right? Energy is 1/2 mv squared. So let's go back and just talk about why we want to develop arc jets. So it didn't take long for researchers in the US and other spacefaring countries to understand that when you have a craft going fast in the upper atmosphere, it could be pretty detrimental to the craft. So there were heating issues that needed to be solved quite quickly. So they went ahead and said, well, we can't throw something up in the sky all the time to test. That's just not practical. So they figured, well, we'll bring the environment down to Earth. So that's where ground facilities come in. So they basically started using blunt bodies in different types of ranges. So there's like ballistic ranges and shock tunnels. NASA uses both of these. But these guys have very short like residence times. Like you get all your data in a shock tunnel in like a milliseconds. So it doesn't really help with the TPS, the thermal protection system materials.
Can you give an example of a blunt?
So a blunt body is like just the shape of, I'm going to show some pictures actually, but it's the shape of the TPS on the rig. I'll show pictures. So in the mid-1950s, arc jet facilities were starting to be designed in the US, and like a lot of our technology at the time was based on German designs around World War II period. So what are the main applications today? Simulating aerothermodynamic heating for entry. This might be the main focus of our arc jet. And then doing so, we could test thermal protection system materials. Then we could develop diagnostic techniques as well, because a lot of these plasma physics environments are not well understood. So there's always good research to be done to understand those and see how those correlate to simulations. Real world testing is always useful for that. And then lastly, this is not the most common, but simulating combustion and air breathing engines operating at hypersonic speed. So Our facility probably will not be used for this, but there's always that possibility as well. So here I just want to talk mainly about some of the uses for the ArcJet facilities, specifically when it comes to TPS testing. I don't really want to focus on like my results here. That's not the main thing I'm trying to show. Just trying to show what can be done with it. But feel free, of course, to ask any questions about this. But what you're basically looking at when you have a TPS and you put it in an ArcJet, you have your ablative material. So ablative material encounters this very high enthalpy, high energy flow, and there's a bow shock that develops here. And so that bow shock plays a large role in dictating the heat loads over the body here. And so, you could see basically how we had high temperatures in the shock here. And basically, we look at this and we could go ahead and get temperature information or recession rates from the ablative material. So emission spectroscopy has been very useful in understanding the constituents that make up the ablative material when it encounters a flow. So this was taken from work I did about 10 years ago at NASA Ames when we were looking at TPS material in a small ArcJet, fiber form. I'll also talk about these a little bit later, Pika and tough rock. And you could see using spectroscopy, we could see some information about the emission spectra, what's inside the ablative material as it ablates from the high heat loads. And we could see the bands at the different wavelengths. Yeah. Sure.
Most of those seem to be alkaline metals,
Yeah.
Potassium, needs.
So these are part of the ablative material. That's a good question because oftentimes it's also not clear when you have an ArcJet. Actually, I'll show this. You'll see that some of the electrodes, they wear into the flow. So there could be particles of copper and things like that. So it's important to know if your flow is contaminated by things like that. So that's another reason why you want to take a good spectra and everything. So other useful techniques, we could use non-contact temperature measurements for obviously looking at the temperature profile. So two-color infrared pyrometry. We did some work using this at NASA Ames to get temperature profile of our TPS. So this technology is completely non-intrusive. You just basically take a pyrometer and you have to set it up and correlate it so it could treat the object, assuming it's a gray body, and actually get correct temperature data. There's some calibrations you have to do. And there is some temperature error associated with the two-color infrared pyrometry. Basically, that's proportional to the temperature, the average wavelength of the two bands. So there's two bands that this uses, which does a good job of basically using the two bands gets rid of the uncertainty due to like dirty windows or contaminants in the view. You don't want any of that, obviously. So that's why I use two-color pyrometry. But anyways, here's a general expression showing that. And along with the pyrometry, we could use infrared photography. That could give us nice contours to see the recession rates in the TPS material and have a good 2D surface map of that. So that's another optical method. And then obviously, I'm not going to go through these different types, but just to be aware of other types of techniques to understand the flow. A lot has been done in ArcJets, especially miniature ArcJets, where you could throw more probes in without worrying about them getting completely obliterated. So you could take heat flux measurements. Here's a picture at NASA Ames. In our miniature ArcJet, we put a guard-on gauge, and basically the guard-on gauge could take radiation. So it takes this radiation and it could translate it to a voltage output, which is proportional to the heat flux. They're pretty simple devices. So you could get the heat flux here. And there's all sorts of different information you could get about the plasma using direct measurement, like stagnation pressure, species concentrations. If you want to look at the actual like electrons, there's questions about the electrons. You could do Langmuir probing. So Langmuir probing will give you information on plasma potential, electron temperature, and electron densities. You could do all that. There's different Langmuir probes. Actually, this is a Langmuir probe we put inside the chamber. This is a triple probe, and that gave us electron characteristics. So don't ask me how all of these work. I don't know. I haven't done all of them, but a few.
So is that a photograph, are those two photographs of the heat jet? That's what you're...
Yes, here's the, see, it's going vertically in this case. Here's the exit, and here's the plasma column, and I'm striking the probes here. Oh, I see it. Yeah. We could step back now and talk a little bit about the actual thermal protection materials that have been used. There's a big history behind all of this. So NASA's been using it way back for Apollo heat shields. They use what's known as AVCOAT. And I believe they still are going to be using that or a variant of it on the upcoming Orion heat shields, which is using a lot of Apollo legacy technology. So here is basically, you could see the before case, and then afterwards you throw it in, and you could just see how this reacts. And obviously, it gets charged quite good, but it does its job. It takes in the thermal radiation, absorbs it, chemical reaction, and it protects your spacecraft. So there's AVCOAT. Other forms are PICA. This is a phenolic impregnated carbon ablator type. And then SpaceX also has their own kind called PICA X. Yeah. So I think they claim it's easier to manufacture and a lot cheaper. I don't know precisely like how much different it is, but for people who don't know, like think SpaceX and NASA are competitors, it's not true. They work together. So they use this PICA material a lot. And so here's another pictures of that. This was PICA we put into the small arc jet at NASA Ames. And space shuttle titles have also been tested as well. So why do we need small scale arc jet facilities? Well, megawatt scale facilities are quite rare. In fact, there's only, I think, 4 or so in the country, 2 at NASA Ames. I think Boeing has one, and NASA Langley has one. So the main ones are actually real close in the Bay, the IHF facility and the AHF facility. These are megawatts and are incredibly expensive to operate. If a customer wants to come in and test something in their arc jets, it'll probably be upwards of $100,000 for a day of testing.
You may have mentioned, sorry, but roughly like how big are we talking? Are the facility?
As far as like the test section size, they're big. You could go in it yourself. I don't know the exact dimensions, but way bigger than the one I'll show you for ours. But yeah, they run at about, I think, maximum 20, or I think the IHF to go to 60 megawatts. Yeah, they're pretty amazing.
And how many watts are are you normally dealing with in terms of like thermal energy for re-entering the atmosphere?
So it depends on the velocity of the spacecraft. So like when we're looking at, I'll show you, I think I showed it, Stardust came in at 12.9 kilometers per second. So that's a good question, but I would assume that they do as good a job as you can of recreating that. So it's a lot of energy. Yeah, sure. A ton of energy.
So you want to be able to like maybe even go a factor of 2 or 3 higher than you would sort of enter most.
Yeah, they could be overkill. That's a good question. It's hard to say. It depends on the application.
When the NASA facility, how big are these things again? Are they the size of this desk?
No, so they're like a whole room. You could think they'll take up. I mean, in length, yeah.
Okay.
You could
Like-
go inside of it. They're
You're
pretty
walking,
large.
I see.
Yeah, I should add a picture of it.
But these are pictures of.
This is the
these-
small
Okay.
miniature ArcJet, yeah. So, due to these limitations, there's been interest in the development of smaller facilities. So NASA has smaller facility. It's called the M-ARC, and then they have a second generation one with a larger vacuum chamber. Still using the same heater though, actually. That's called M-ARC2. The University of Oxford is developing one called the OPG-1. And I think some universities around the country might have also dabbled with them. But the idea is small scale facilities share much of the same research promise as high powered, but require way fewer operating personnel and maintenance. So they're essentially good screening facilities. So if a school or company wants to test something, they could do it quickly in a small one. And if they really want to go further, then they could go ahead and scale up if they want. So that's the project. So yeah, they accommodate projects with lower budgets and could be good for long-term projects where, again, they just want to iterate on some design or something, and they could just keep trying it and get quick, fast turnaround and information that way.
So if like the megawatt test costs about 100,000 or on the order of 100,000 a day, would the kilowatt ones cost about 1,000 a day, or what's the scale?
Yeah, that's a good question. It'll be definitely a lot cheaper than that. You could probably run these ArcJet facilities with 1 or 2 personnel.
Yeah.
The power requires way lower, so it could be order of magnitude lower for sure. And that's the whole promise of it. So here's the design of the facility from a large view. So it's called the RDMS Research Development and Material Screening XJet Facility. So here's the power supply. So this is an off-the-shelf arc welding supply, Max Pro 200. It's capable of up to 30 kilowatts, which is still a lot of power. And so that's the power supply. We have a roughing pump to get the chamber to vacuum. Background pressures before ignition or arc heating should be in the upper millitors, a few hundred millitors, hopefully no more than a 4 for the vacuum. As the roughing pumps. Deionized water comes into the chamber to cool. We have to cool the anode, and the cathode's cooled as well, which won't show in the diagram, but the cathode is cooled. Here's a pump to move the water, chiller, cool it. And so there's a circuit here of the water going through the heater, which I'll show on the heater soon. Here is just data acquisition. Again, we could put spectroscopy, pyrometry, oscilloscope information. We have all this available for customers or whoever wants to use. And a PC data activation there. So one thing about our ArcJet is we want to incorporate a 2% thoriated tungsten cathode, so it could run cool and longer. That's one of the life-limiting mechanisms of ArcJets and actually any like electric propulsion. The cathodes wear out because they're experiencing temperatures upwards of like 3,000 Kelvin constantly. So it's very high temperature, and thoriated tungsten has a low work function, so it could do the job and actually decrease the temperature over tungsten by like 500 or 600 degrees. We'll use a custom built stainless steel vacuum chamber that'll house everything. You could get these actually quite easily from like Leicester. And we'll have linear actuators to insert samples or gauges or what have you into the plasma. Actually, we're going to upgrade to a larger chamber. This is an older picture, but same idea. I'll talk a little bit more about it.
What has to be a vacuum if you're putting air in?
So you want a vacuum environment to kind of recreate what's going on in the upper atmosphere. You don't, right? Obviously, it's a lot less dense. Also, when you have an arc discharge between the cathode and anode, you don't want too many particles that inhibits arc attachment. You want them to be able to go easily. So you want to get it as like a vacuum. So here's a look at the vacuum chamber. It's a small vacuum chamber, but again, we're going to upgrade this. This one shown is 36-inch length by 30-inch diameter. So it's hard to work with. There's a lot of stuff you have to put into that small space. We're going to double the length. So we're going to go to a 60-inch length vacuum chamber with more windows and things like that. But basically, here's a look at it. Here's the arc heater here. And here's a cross-sectional view of it. But here it is, the plasma column. And so we'll have an actuator where we could put our sample, and hopefully we could program it. We'll put a adjustment motor where we could change angle of attack. So we could tilt our TPS and look at shearing, different things.
Is that part of the reason it's had it be longer is that you can essentially move the sample back and forth to see you can vary the intensity that way rather than changing the actual electronics?
There's a lot of benefits to making it larger. One of them is you have more flexibility. Yes, we could move this around. We could go further back. The main reason is the heat loads. This chamber is going to get quite hot, and even if you water cool, you don't want to worry about that. So making it larger, even like 3 more feet, will change the volume drastically. So
like the whole time the experiment was going, it's the outside of this vacuum chamber is just being.
Oh yeah, it can the chamber could heat up. Yeah, we would cool it. You could put like cooling channels, but the vacuum chamber, yeah, without cooling would be hot to the touch quite quickly. So yeah, here's the plasma column, gas line. So everything just coming through here. And here's a cross-sectional view. So we have our thoriated tungsten cathode. Insulation. So we have to insulate properly so there's not unwanted arcing. So we insulate the cathode. And then here's our copper anode. This is the key component that needs to be cooled or it'll be obliterated quite quickly. So we have a channel here, high flow rate of cooling. Yeah, so that's the view of it there.
This is a big spark plug. It's a big spark plug.
It's an arc. It's like an arc welding
Yeah,
supply.
yeah.
It was with a plasma column and a converging, diverging output. It's quite simple in that respect.
Where is the gas coming in that cross section?
It should be coming in through here and coming out. Yeah. There's a swirl ring also that will make sure it's distributed well. So I could show a video of this was taken 10 years ago. I took this at the NASA MR, so you guys could get an idea of what it actually looks like running.
Yeah.
So yeah, here's pictures just for curiosity of what happened to the fiber forms. So you saw it was only about 20, 30 seconds. So you could see a lot of recession. Small sample, so unfortunately we can only work with small samples.
So it looks like first you gotta get the gases going, and then you shove the sample into it. Is that what happens?
Yes. So arc jets are difficult because it's also hard to get great repeatability. So you want to wait a little bit to at least let it run on its steady state and then do it, and hopefully you could get repeated results. If you just do it right away, you're going to get all that copper.
Yeah.
So this is what we saw for the fiber form. Here's some temperature measurements. So you could see because it started to just ablate, it actually reached its maximum temperature in about 4 seconds, and that's it. So fiber form is a precursor to pica. It's carbon. Pica is a little bit better. I mean, it's what they use on a lot of heat shields. So it ran a little cooler. This was another material I'm not familiar with called tough rock.
When you said it was making diamonds, is it making real diamonds?
Like shock, no, it's like shock diamonds in the gas, like you could see that. If you ever looked like maybe at an SR-71 Blackbird out of its jets, there's like shock diamonds.
It's just the shape of the flume, yeah.
Yeah, it's like because the flow is going supersonic.
Is the shock diamond different for shock flow? Or is it just different for the same thing?
I think it's the same. So yeah, here is now the work we've been doing. So all that was stuff done years ago, not from us. And now here is what we're doing, our modeling. So we have a team that's been working on doing flow simulations for our nozzles so we can understand what's going on. So we've had some good results. Basically, we're looking at this through the center line from the cathode exit. So we have the cathode exit right through the plasma column here out the exit. So this is what, not even a 1/10 of a meter. So it's a small arc jet here.
Now, when you're saying simulation, are you doing math models or?
Yes.
These are math models?
Yeah, this is using Anson fluid 2D solver. So there's some assumptions we have to put in. We assume laminar flow.
Okay.
And different kinds of gas modeling equations.
Okay, great. So in what I've learned from some of these other seminars is that physicists talk about simulators. There can be another kind of simulator. It can be labs, and it's actually labs in something else.
So what we're doing here is pretty common in fluid dynamics. These are CFD simulations.
Very good, thank you.
Yeah. Actually, it's really nice now. There's these programs like ANSYS. It's way more user-friendly. Like someone could almost go on and YouTube some things and learn how to use it. Whereas back in the day, forget it. So we use that. Here's our boundary conditions. We did these up for argon. We have to do it with air. We'll do that later. So argon mass flow between 0.2 and 2 grams per second coming in. Inlet stagnation pressure is 160 Pascal. Inlet stagnation temperature, 3,700 Kelvin. So this is based on prior information in the MR. So we use these for boundaries. Vacuum pressure, this is obviously not totally correct, but we just put 0.
That's not good.
Yeah. And background temperature, 300 Kelvin. So we can see the ratio of the pressures versus stagnation pressures is falling quickly, and we'll see the contours, and it should show it better. Falls quickly from the arc discharge through the column out the nozzle. Same thing with the temperature ratios for the different flow rates. So here are the flow simulation contours. So this is our cathode here. This is I guess you can say the combustion chamber, the column here, and then the nozzle. So temperatures are very high here, as we would expect, and they decrease decrease normally throughout here. So here's our temperature profile. And velocity, good results as well for the velocity. This is like a different idea. The velocity is actually quite slow at first, right? The gas comes in, and then it's accelerated, like we said. And so that the key thing you want is to make sure it's choked here. You want a Mach number equal to 1. That way you could accelerate. Because when you're thinking of like a hose, for example, if you want the flow to go faster, you pinch down on it, right? But that is for subsonic environments. For supersonic, you have to open the hose actually. So that's what we do, open it up, and we can see the velocity increase.
So a question related, I guess somewhat related to this, maybe you can cover it later, but what's the design process for particularly this component like, and did you guys machine it in-house or did you find somebody else to do it?
So it hasn't been actually machined yet. So we are working with a machining company called Rapid Access who will do it for us. We're actually still fine-tuning things, but this is a general idea. Yeah.
What's the difference between the two? You know, obviously they're very different. What made them different? From the top view to the one below it. Why is it red in one place and another?
No particular reason. We just want to have the contour so you could see the difference. I don't know, red being like a high number, blue being low.
One is temperature.
But one's temperature and one's velocity. Yeah. Sorry.
Thank you. I got it. Okay.
Yeah.
Thank you for clarifying.
Yeah, they're different things. But I mean, the velocity could have been the same color.
Yeah,
So
no, I got it. I thought you were,
there's no reason.
I thought it was temperature.
So here's the pressure profile, kilopascals, same idea, and enthalpies. So these are important parameters in an arc jet. So that's our modeling. Hopefully it's good. We're going to compare it to what we do. We'll put in some of those probes in and see if our models predicted well, and we'll iterate if necessary. And here is basically the heat transfer analysis. So we have this is our whole arc jet heater here now, right? So this is the exit here. It's just going up. So we can see most of the heat where we would expect is right at the discharge region. So we have high temperature. This includes cooling. That's why it's not super duper. We're cooling this. I don't have like the cooling line shown, but that's the idea. So high temperature, and then lower temperature as it goes out. Heat flux, same idea. So here again is our assumptions. Our coolant water flow is at 0.1 kilograms per second. Coolant water temperature is 15 degrees C because we're going to use a chiller. Here's some information if you're into the fluid mechanics. We're assuming transitional flow. So that Reynolds number is in the 6,000 range. So we use this Nusselt expression for that. And our convective heat transfer coefficient H. This was also taken from data for other systems, 2,700 watts per meter squared Kelvin. And here's, again, the other things, emissivity, copper, 0.05. So basically, also an important thing we looked at is the temperature with time profile, the nozzle temperature. So at about, I'd say, right, like this shows here, 60 seconds, we reach this maximum temperature. So given our current system, you could see that although the temperature increases quickly, it starts to level a bit, but it's still increasing. I mean, so again, small space, you run for minutes or half an hour, this is going to keep going. So that's not good. So with this configuration, we probably only run for like a minute. But again, we're trying to upgrade, so maybe we could go to 15 minutes or something like that.
Doesn't ask, like, how long can it theoretically go for?
Well, as long as something doesn't break, so as long as you're...
The cost benefit then.
The question is what's going to fail first? If the anode, the cathode, the probes that you're using will fail.
Would the idea be to like have a cooling time like in between runs and then have like multiple samples loaded in like on a rotation or something? Like,
Yeah, so that's a good point. I didn't address that with your first question about using a small chamber, why a bigger chamber. The other thing for using a big chamber, most importantly, is the accessibility. Using a small chamber could really take a long time to fix things. So you want that big chamber, you could go in there, cool it quicker between runs and do all the maintenance you need to do. That's also.
and like how much do you have to pump down? Like is it that like Militor?
Like I said, you should be fine at without gas running in the upper millitors, 300, 400, 500.
Oh, okay. So it's not like a crazy pump time. It's like maybe up a few minutes.
Yeah, it shouldn't take that long. Yeah. Maybe half an hour at the most, not even that.
You gotta ask, the water flow rate, that looks like a garden hose can supply you all the water. Kilograms.
Yeah,
10
well,
kilograms.
we're constrained by the pipe diameters, so.
No, I'm saying
Yeah.
you don't need a fire hose.
Oh.
To bring in all the water you need.
Oh.
To keep it cool.
Mm-hmm. Yeah, I mean, we just want a consistent flow rate and chill it. But yeah, you don't need a ton of water. It works quite well with these type of things, actually. It's amazing how much just like even room temp, just some water just changes everything. If you don't put any cooling, the anode just will melt.
Question, I don't know if you know this, but do you happen to know the typical length of time that a spacecraft spends in reentry at high temperature? Related to the
again, it depends on the application. I talked about that stardust.
Is that just have a higher? It's coming from a higher.
Stardust came at a steep angle, and I don't know. It was going like super fast. Actually, they slowed that thing down like 30. It went from 30 Gs to like almost nothing in like minutes. So that's that application. So it's hard to say, but minutes. It depends what you want to do. If it's a manned craft, obviously you can't. It's just do that. Yeah. So I was like that movie Apollo 13. They showed like when they were in blackout, and it was like in the movies like 10 minutes.
Oh, I see what you're
saying. So that's the system. So again, in our future studies, we're actually going to take our models and characterize the actual environment and compare those. Like I said, that's essential for obtaining useful experimental results, as well as comparing it to the computer simulations. So we're going to try to look at the heat flux, the enthalpy, stagnation pressure, species concentrations, and all these. These are the type of things anyone who uses our facility might want to know as well. They want to know, obviously, the conditions. And I've already talked about this, but we'll use different types of intrusive techniques and non-intrusive techniques to do that. So again, this just outlined the construction of that facility. This will fulfill a need in academia and industry for high enthalpy plasma research, as well as TPS material testing. So when this is built, any physics students studying plasmas, if they want to do some actual real life testing, that's a possibility. And then our preliminary designs, computer-aided designs have been done. We've looked at costs, which I haven't showed, and a bunch of simulations for the X-Jet. So hopefully it'll be a strong candidate to compete with the MARC and NASA, which doesn't actually typically use customers. They usually just use it for their own research. But we'll use that, and it'll be one of the few built in either academic or government research laboratories in the country, or actually in the world. There's not a lot of them. I think that's that. A little more.
You got some more conclusions. Yeah.
It's my question. It's like, well, where is this thing? We've been on Zoom land.
Yeah. So our investigations showed that it could create a flow about Mach 3, bulk enthalpies of near 3 megajoules for the 30 kilowatt power supply. So yeah, where is it going to be built? Well, we want to do it locally near here. So we're looking to find our facility. We've made good progress on that actually lately. It'll be in the peninsula, so not East Bay.
Union Square could use it.
Well,
Now, all the shopping centers are closing down.
maybe now's the time to make a deal. I don't know. So we'll hopefully get going in the late this year, or it might leak into early 2025. And hopefully we'll be really going by 2026. That's our goal.
You already have like people who are interested in like what you're doing, wanting to work with you once you get started.
Yes, we've been working to get letters of support. We've got a good amount from universities and industry as well. So there has been a need for this, and we've done a lot of research in that area. We're happy with the results.
So yeah, I have like, how is this getting funded, right? And are there like competitors other than other private,
I don't want to go
that are...
too much into that. Okay. I could just say it's basically a lot of VC funding or partnerships.
Okay, yeah.
Actually,
that's fine, yeah.
To get the system running, you do not need that much money, actually. You don't need a lot of personnel. The technology, a lot of it's off the shelf. So the idea is it could be sustainable quickly, hopefully.
So this is like private money coming in, and you're not like, like sometimes DOE or NSF and stuff has like grant opportunities.
There's SBIRs.
Yeah.
There's SBIRs or STTRs if you want to work. That's the same, but you work with universities.
Okay.
We've applied to those, but not for other things. I honestly don't like them.
Yeah. Okay. Yeah. It's fair enough.
It's a lot of work.
Yeah.
And it goes into a black box. But anyways.
One potential application, I don't know if the temperatures are even high enough for like testing nuclear fusion, containment, and things like that.
Maybe that's something I have not looked into. Okay. Probably would want a bigger chamber. But
you probably just testing like individual components of walls and things. I think interesting business case. With all the VC money coming into fusion right now, there might be some money.
I wouldn't count anything out that if we could do in our arrangement.
Earlier, you mentioned the thorium in the cathode on lower the work function. Why?
So lowering the work function means you could emit those electrons off the surface without as much work, as you don't need as much current or energy.
Oh, it saves power.
Saves power, and they run at a lower temperature. Both, it's better. Also, when you take a cathode and you first start the arc discharge, that's the most damaging thing to the cathode, because the arc is running around the cathode trying to attach. There's really high pockets of high current densities along the cathode. So if you could run it cooler, obviously it helps its survivability.
Oh, you've got like, sort of like a points on the cathode at first, sort of like.
Yeah.
And that's, yeah.
I'm trying to find a good.
The idea is the arc will attach near the tip, but
yeah, right.
Oftentimes it goes all over the place, and then finally.
I suppose those initial kind of pointing things is part that causes sputtering first, and then things sort of spin the cathode sort of smooths off.
Yeah, and I mean usually you might want to put a tip on it because it helps.
Let's thank Doug, because this has been really. Anybody else have any questions?
Okay. In terms of cooling, is there a reason why I don't know, not you, but the project chooses to use water versus something like an oil or
I mean you could use glycol maybe or something like a refrigerant. You probably don't need that much cooling, it's just easier to use. All you need is a tank and ionized water. That's the main thing.
Doug, is this like an offshoot of what you did your PhD thesis on, or is this like a side project you picked up after?
So actually, my PhD work was on cathodes for MPD electric propulsion thrusters.
Ah.
And then I worked at NASA for a couple of years on their miniature arc jet. So that's where I go back.
Have some snacks in 236. You think yes?
I think so.
I didn't come and check. I think so. We go on over there. Okay, thank you, Doug.
Yeah, thank you.
Yeah, thanks, Doug.
Thank you.